Hi everyone, welcome back to our second part of this lecture for this week. Okay, so we have discussed the virial equation of state and the definition of the compressibility factor. So now let us discuss another equation of state. Okay, and these equations of state now collectively known as the cubic equations of state. And these are simplest types of equations which are capable of representing both now the vapor and the liquid root. Kasi doon sa ating virial EOS, okay, vapor root lang yung nakukuha natin. Okay, so applicable na siya for the vapor root. However, for the cubic equations of state, these are applicable for the liquid root and the vapor root. Okay? So if you take a look at the PV diagram for a pure substance, okay, recall this again, meron tayong two-phase region. Okay? So the cubic EOS is a good representation on how to get multiple roots. Okay, so at T is greater than critical temperature, recall the behavior of our molar volume in terms of pressure is always monotonically decreasing. Okay, yung isotherms natin, T is monotonically decreasing. Okay, at T is equal to Tc, we have a horizontal inflection point. Okay, and this will be useful to us when we're deriving some constants for the cubic equation of state. Okay, however, for the cubic EOS, okay, below the critical temperature, nagkakaroon tayo ng fluctuation. Okay, nagkakaroon tayo ng isang local minima and isang local maxima due to the nature of a cubic equation of state. Okay, so in essence, unrealistic tong behavior na to. Kasi diba, dapat ang nangyayari kapag cubic EOS, okay, ito dapat yung na-trace natin na isotherm. So, decreasing, tapos flat, tapos tsaka siya magde-decrease ulit. Okay? However, for the cubic EOS, okay, it can predict the actual two roots, okay, to good accuracy. Pero yung behavior sa loob, hindi maganda. Kasi meron tayong local minima and local maxima. However, this local minima and maxima will become actually useful later to us. Okay? So with the cubic EOS, we can now obtain both the liquid root and the vapor root for a saturated mixture. Okay? And above the critical temperature, okay, we can obtain a real root only. Kasi ba, P, isa lang yung volume. Tapos the other two roots are possibly imaginary na hindi natin gagamitin. And the simplest cubic equation of state that we have available is known as our van der Waals EOS. Okay, and the van der Waals EOS now has two terms, okay, which is a variation from the ideal gas law. Meron tayong term na A over V squared, which accounts for the molecular interactions. Kasi diba, sa ideal gas law, ina-assume natin na walang interactions yung mga gas molecules. And B, ngayon, we can now account for the actual volume of each molecule, or the total volume of each molecule per mole of the gas. Okay, so the van der Waals EOS, so given the following, P plus A over V squared times V minus V is equal to RT. And you can also rearrange the van der Waals EOS in this manner. Ayan. So you have a cubic EOS of which two may be complex, okay, especially if you're above the critical temperature. Okay? However, pag nasa below the critical temperature ka, you have an unrealistic behavior in the two-phase region. Okay? And recall that the values of V should always be real and positive and should always be greater than the constant B. That is very important. Okay? Kasi diba, B represents the total volume of the gas molecules per mole of gas. Okay, so dapat the volume of the gas should be much greater than the volume of B. Tapos the volume of the liquid, kung liquid root yan, should be approximately close to the volume of B. Okay, so now, the challenge now for the van der Waals EOS is how do we determine the constants A and B? Okay, so it's one thing na pwede naman to i-tabulate. However, we can now make use of one critical point, okay, which is the critical point in here. And the behavior of the critical point is that we have a horizontal inflection. And the horizontal inflection now, coupled together with the van der Waals EOS, will give us a way to obtain functions for A and B in terms of the properties of the actual fluid that we need. Okay, so imbes i-tabulate natin, we can now actually have derived equations for both A and B for each gas. Okay, and this is now tied together with our critical point. And how do we make use of this? So at the critical point, we have a horizontal inflection point. And recall from your math that the horizontal inflection point means that you have, okay, the first derivative with respect to pressure. Okay, so dp partial of p with respect to v at constant t, which is tc, is equal to 0. And the second derivative at this point should also be equal to 0. Okay, so from here, we can take the first and second derivative of your van der Waals EOS with respect to pressure. So take the derivative of pressure with respect to volume. Okay, so we have the first derivative, which is equal to 0, and the second derivative, which is now equal to 0. Okay, so we now have two equations. Okay, and we can now express A and B as a functions of the critical point. So para gawin yan, so from the first derivative, let us do some manipulations. Okay, like we can multiply both sides by 2 over v minus b to obtain the following expression. Okay, and from the second derivative, recall na ito yung expression natin. Okay, and if we add these two equations, okay, kung pinag-add natin yan, we can cancel these two terms, will now cancel each other out. Combining these, you have the following expression. So for a over v cubed times v minus b minus 6a over v to the fourth is equal to 0. And we can simplify this further. So v cubed tanggalin na. So magiging v na lang siya. Okay, so simplifying, you can get 2 over v minus b minus 3 over v is equal to 0. Okay, and rearranging this and simplifying, you can get 3b is equal to v. Okay, or b is equal to 1/3 times v. And since nasa critical point tayo, okay, these are evaluated all at the critical point, okay, the constant b is now just equal to 1/3 of vc. So the constant b, which is the total volume of the molecules per mole of gas, is equal to just 1/3 of the critical volume of our fluid or of our species. Okay, so meron na tayo ngayong term for B as a function of the critical properties. Okay, and the critical properties are tabulated per species. So now let us obtain an expression for A, okay, in terms of the other critical properties. Okay, so in order for us to obtain an expression for A in terms of the critical properties, balik tayo sa first derivative expression ulit. Ayan. And in the first derivative expression, we can now substitute B is equal to 1/3 Vc. Okay? And substituting this and simplifying, you can get this expression. Yeah? And then you can now isolate for A. Okay? Isolating for A, you can get A is equal to 9 Vc RTC all over 8. Okay? Or, you can now substitute B here kung gusto natin. So A is equal to 27 BR TC divided by 8. Ayan. So from here, pwede na tayong maging content with this kasi meron tayong A as a function of VC and TC. Okay, however, minsan gusto natin i-express in terms of T and P lahat. So let's express this in terms of TC and PC instead of VC. Okay, so in order for us to do that, you can now substitute this into the van der Waals EOS. Okay, so PC is equal to RTC over VC minus B minus A over VC squared. Okay, and let's substitute and the expression for B na 1/3 VC, okay, to obtain this expression now. Okay, and simplifying this, okay, you can get the following. Now PC is equal to 3R times TC all over 2 VC minus A over VC squared. Okay, next up, substitute na ngayon natin si A, which is 9 VC RTC all over 8. Okay, so substituting this term for A dito, you can get this expression. Okay, and again, do some further simplifications. And simplifying further again, you can now have PC is equal to 3RTC all over 8 VC, or rearranging PC times VC all over RTC Again, ito, PV over RT is the definition of the compressibility factor. Therefore, ZC is equal to 3/8. Okay, so what the van der Waals EOS is saying now is that the compressibility factor for any possible chemical species is just equal to 3/8. Okay, so in real life, hindi talaga ZC is equal to 3/8 for all species. So, nagde-deviate yan sa 3/8. So, the van der Waals EOS, okay, is the simplest cubic equation of state that we have. Okay? So, medyo okay naman yung nakuha natin na roots. Okay? But they're not the most accurate. Kasi, diba, the van der Waals EOS approximates now that the compressibility factor at the critical point is 3/8. This is not the case. So, nag-vary talaga yan. Okay? So we have actually other cubic equations of state which are more accurate in nature. Pero for the simplest cubic EOS plus the van der Waals, we can, medyo maganda naman yung nakuha natin na results. Pero hindi sila yung pinaka-accurate. Okay? So from here, we can now express A in terms of PC and TC only by substituting this whole expression, okay, or manipulated expression, such that A is now equal to 27R squared times TC squared over 64 PC. So now for the van der Waals EOS again, you can now have A and B as a function of the critical temperature and the critical pressure. Okay, so dito, pansin natin, sinubstitute natin, imbes na 1/3 VC, so 1 over 8 RTC over PC na lang. Okay? Where for the van der Waals EOS, all gases can be generalized such that ZC is just equal to 3/8. Now, for the van der Waals EOS, be mindful of the units. Okay, so A should always be pressure times volume squared all over mole squared, and B should always be volume per mole of gas. If you want to evaluate this in terms of the total volume, so P is equal to RT over VT, so total volume na siya, minus NB, okay, minus N squared A over V total volume squared. Okay, so may factor tayo na N squared for A and N for B. Okay, so let's now consider this particular example. So we want to calculate again the real volume of isopropanol vapor and syempre the compressibility factor, okay, at 200 degrees Celsius and 10 bar. So parang ito yung ginawa natin doon sa viral EOS, but this time using the van der Waals EOS. And for the van der Waals EOS, we would need the critical properties, which are the critical pressure and the critical temperature. Okay, so first and foremost, okay, so syempre, ideal gas constant, yun pa rin. You need to calculate the van der Waals constant. So A and B. Okay, so first, A is equal to 27 R squared times TC squared over 64 PC. And you can now get A to be the following value. And B is equal to 1/8 RTC over PC. So B is equal to 110.93 cm cubed per mole. Now, let's substitute this into the van der Waals EOS, okay, and rearrange into a cubic equation. Okay, so ito yung one way to solve by rearranging cubic equation of state siya, so we can arrange this into a cubic equation. Okay, so substituting the van der Waals EOS and rearranging. Okay, so ilagay natin to dito. Okay, and ito dyan. So if you rearrange this, ito yung magiging working expression natin. Okay, or more generally, ayan, so pansin natin, ito yung coefficient for cubed, the coefficient for the squared term, coefficient for the one term, and the constant. Okay, so from here you can now solve for the molar volume. Okay, or kung gusto nyo mag-shift solve, use the ideal gas volume as your initial guess. Okay, so from here, if you solve, you can get V is equal to 3621.16 cm cubed per mole. And the ideal gas volume is 3933.77 cm cubed per mole. Therefore, our compressibility factor is 0.9205. Okay. You can also use the van der Waals EOS to obtain actual work done, okay, for some processes. Okay. So from here, let's say you have the isothermal compression of nitrogen gas. from 1500 kPa to 98 Kelvin. Okay, and now determine the final pressure of the gas if the work done on the gas is 5,000 joules per mole and the gas obeys the van der Waals EOS. So let's obtain the van der Waals constant. So you should know how to do this by now. So A should be the following value and B should be the following value. And let's now use R to be 8.314 kilopascal meter cube per kilomole Kelvin. Okay. So now, how do we obtain the pressure? Kasi kung ideal gas to, diba? PV is equal to RT. Okay? But for the van der Waals gas, P is equal to RT over V minus A over V squared. And the work term for an ideal gas, or any gas actually, work is always negative P dV, or negative P dV from V1 to V2. Pag ideal gas, si P in-express natin in terms of RT and V. Okay, kaya lumalabas pag ideal gas, negative RT ln V2 over V1 is yung work. However, using the van der Waals EOS, hindi na pwede na negative RT ln V2 over V1 kasi iba na yung equation of state natin. Okay? So from here, the work term, negative integral of P dV from V1 to V2, yung pressure term natin should now be the whole van der Waals EOS. Okay, so to solve this, first, kailangan muna i-calculate si V1. So, calculate muna si V1. So, using the van der Waals EOS, okay, you can get V1 now to be 1.6358 meter cube per kilomole. Okay, and next step natin is, okay, alam na natin si V1. Okay, we know the work, which is 5,000 joules per mole. We need to get V2. Okay, so we need to get the integrated expression of the work term using the van der Waals EOS. So let's integrate the work expression. So 5,000 kilojoules per kilomole is equal to negative integral of P dV, where P is this whole expression. Okay, in terms of the volume na lang, okay, T and A are constants kasi T is constant kasi isothermal yung expression natin. Okay, so from here, para ma-solve si V2, integrate muna natin to. Okay, so integrating, you can get the following expression. Alright, so you can now just shift solve for V2. Okay, but make sure na medyo maganda yung guess natin. Kasi diba, si V1 is 1.6358, so make sure na yung guess nyo ay slightly less than 1.6358 para mag-converge sa correct value. Okay, so solving, you can get V2, which is 0.2066 meter cube per kilomole. And substituting this back into the van der Waals EOS, you can now calculate the final pressure. And the final pressure now, okay, substituting, is 11,536 kilopascals. So we have, okay, an increase from 1,500 kPa to 11,500 kPa, which is approximately a 7 to 8 times increase in pressure. So 11,500 kPa, medyo mataas yung pressure. So hindi ito mag-work kapag ideal gas lang yung in-assume natin. So mas accurate ng konti yung magiging solution if we use the van der Waals EOS. Okay. So now, one limitation of the van der Waals EOS is that ina-assume niya na lahat ng compressibility factor at the critical point for all species are the same, not 3/8. Okay. However, this is not always the case. Okay. So now we have a new theorem known as the theorem of corresponding states. Okay. And this is now related to deviations with respect to the critical point of our substance. And the theorem of corresponding states states that all fluids with compared the same reduced temperature and same reduced pressure should have approximately the same compressibility factor, and all deviate from the ideal gas behavior to about the same degree. Okay? So for any fluid, basta similar sa same PR and same TR, dapat daw same yung compressibility factor nila. Okay? So we have what we call two-parameter correlations, which only require the use of two reducing parameters, which are TC and PC. And the van der Waals EOS is one of these one of these correlations, okay, which require the use of TC and PC. Okay. However, this is accurate for simple fluids such as argon, krypton, xenon, the other noble gases, but nagde-deviate sila for more complex fluids. Okay. So with this, meron tayong konting variation of the theorem of corresponding states. Kasi this theorem only compares two properties, TC and PC. Okay, pero hindi niya kino-compare the actual property or the actual composition of our fluid, okay, or the structure of the molecule in our fluid. Okay, and these deviations are highly greater for um, more complex fluids. So may something tayo ngayon sa mga complex fluids na kailangan pang i-account in this theorem of corresponding states. So ano itong deviation na yan? Or ano itong property na yan? So now Pitzer in 1955, okay, had an experiment, okay, na pinlot niya ang log of PRSat, okay, with respect to 1 over the reduced temperature. Okay? And napansin niya na may linear relationship between the logarithm of the reduced saturation pressure with respect to the reciprocal of the reduced temperature. Okay? So for the simple gases, argon, krypton, and xenon, the slope was negative 2.3. Okay? Pero nag-iiba siya, nag-deviate siya further for more complex gases. Okay? And with this, Pitzer defined a new property known as our eccentric factor or omega. Okay? And omega is simply the difference, okay, between this point. Okay? So kung ito yung point for argon, krypton, and xenon, evaluated at this reduced temperature, yung slope, okay, yung value ni log PRSat, okay, is negative 1 at this reduced temperature. Tapos, mina-measure lang yung difference between log PRSat for this same reciprocal reduced temperature for any other fluid. So kung octane, okay, yung difference na yan is the compressibility or the eccentric factor rather for N-octane. Okay, so this eccentric factor is now tabulated together with your critical temperature and critical pressure in multiple appendices. So this can be found in Appendix B of SVA. So from here, you can now have a 3-parameter correlation. Okay, so the theorem of corresponding states can now be modified to include both temperature, the critical temperature, the critical pressure, and now your eccentric factor. So now your 3-parameter theorem should be revised to state that all fluids having the same value of the eccentric factor, when compared at the same reduced temperature and reduced pressure, they should all deviate from ideal gas behavior to about the same degree. And using this and the formulation of van der Waals and cubic EOS, we now arrive to what we call your generic cubic EOS equation, okay, where P is equal to the following expression, okay, where B, A of t, epsilon, and sigma, okay, are functions or constants depending on the EOS and the substance. Okay, so epsilon, sigma, okay, and as well as A and B, which have constants of psi and omega, okay, are constants dependent on the EOS and however independent of the substance. So depende lang sa EOS yung magiging values ng apat na yan. Okay, A of t, okay, A is a function of temperature and B are substance dependent, and alpha TR, which is dito nasa A, okay, is empirically determined and specific per EOS. So ano itong mga iba't ibang cubic EOS na meron tayo? So first and foremost, syempre meron tayong van der Waals EOS, and we can reduce this generic cubic EOS to the van der Waals EOS, diba? Ang van der Waals EOS natin is P is equal to RT over V minus B minus A over V squared. Okay? And we have a function of A and we have a function of B as well. And kung V squared to dapat, kung van der Waals EOS, epsilon is equal to sigma, which is equal to 0. Okay? Yan. So ano ba yung ibang expressions natin for the other cubic EOS? Okay, so another form of a cubic EOS is known as our Redlich-Kwong EOS. Okay, ito yung expression natin where ito yung mga constants or parameters for the cubic EOS. Okay, where alpha TR is equal to TR raised to negative 1/2 and psi and omega are the following constants. Ayan. So, your Redlich-Kwong EOS is a two-parameter correlation kasi dependent lang yung mga values ito on TC and PC. Okay, and you can find these values dito sa table B.1 in SVA. Ayan. Okay, so ito si eccentric factor omega. This is TC in Kelvin and PC in bar. So your van der Waals and Redlich-Kwong EOS, these are your two-parameter correlations. However, diba, hindi ganun ka-accurate kapag two-parameter kasi we don't account the shape of the molecule or the complexity of the molecule. Okay, so to account for that, meron tayong three-parameter correlations. So we also have three-parameter cubic equation of state na mag-factor in na ngayon si eccentric factor. Okay, so for your cubic EOS, again, two-parameter correlations, si van der Waals and Redlich-Kwong. Tapos ngayon, we have the three-parameter correlations kung saan naka-factor in na si omega or eccentric factor sa alpha term natin. Okay, so yielding a three-parameter correlation, we have the suave Redlich-Kwong equation, the SRK, and the most popular equation of state actually right now, okay, which is the Peng-Robinson equation of state. Okay, so now how do you evaluate these equations of state? So summarize sila by SVA through the following table. Okay, so we now have alpha TR, sigma, epsilon, okay, omega, psi for these different equations of state. Okay, and si ZC, okay, dependent, ina-approximate siya ngayon ng iba equations of state. Okay, so 3/8 daw siya kapag van der Waals, pero 1/3 siya sa Redlich-Kwong and suave Redlich-Kwong. Okay, in fact, si suave Redlich-Kwong, ang kaibahan lang niya kay Redlich-Kwong is the alpha TR term. Okay, so meron lang siyang correction factor to account for the shape of the molecule, which is the eccentric factor. And si Peng-Robinson, iba naman yung totally different yung sa kanya. Okay, so alpha SRK for the alpha SRK and alpha PR are the following equations. Okay, so dependent siya on both the temperature, reduced temperature, and the eccentric factor. Okay, now, how do you actually solve the roots of the cubic EOS? Okay, depende yan kung ano yung gusto mong root. So you have either want to calculate the vapor root or the liquid root. So for iterative calculations, okay, so ito yung generic form of the cubic EOS. Okay, if you multiply this by V minus B over RT, okay, and obtain this and rearrange, okay, you can get this expression. Ayan. And this will now give you your vapor and vapor-like root. So gamitin yan, okay, start from initial guess. So guess V is equal to V ideal. So parang ito yung temperature calculations natin na iterative. So guess V is equal to V ideal dito sa right-hand side. Okay, tapos get a new value of the V and then iterate until mag-converge. Okay, so this is what you will do for the vapor and vapor-like root. Now, what if gusto mo liquid or the liquid-like root? So para gawin yon, you should isolate for this particular volume. So rearrange that to obtain this expression. And if you once you obtain this expression, okay, ito na yung iterate natin for liquid and the liquid-like root. So for this, you will guess V is equal to B. So plug in mo si B dito sa right-hand side in terms of, so si V, plug in mo the value of B, and then keep iterating until the convergence. Okay, so to summarize, yan, okay, so you actually have two methods for both types of roots. You have the method na meron tayong dimensions in terms of the volume, but you also have the dimensionless form of these equations. Okay, so again, for the vapor and vapor-like root, you will start with V as V ideal, and then you will iterate. Or if you want to obtain the dimensionless form, okay, which will be more useful later on actually, you should make the necessary transformations based on these values. Okay, so express A in terms of Q and B in terms of beta. Okay, so make the necessary transformations to obtain this expression. Okay, so ito yung dimensionless form ng itong equation na yan. Okay, so with this, you'll now start iterating, but this time you'll use z in terms of iterate in terms of z. So start ka sa right-hand side, plug in z is equal to 1, and then iterate until mag-converge. And similarly, for the liquid and liquid-like roots, you can make the same transformations and obtain this new equation, the dimensionless form, for the iteration for the liquid-like root. Okay, so V was dito, kung ayaw mo dimensionless, so I'd start iterating for V in terms of B muna, and then iterate until convergence. Or, kung gusto mo dimensionless, start an iteration using Z is equal to beta. Okay, and then iterate until convergence. Okay, so now these equations of state, okay, which are expressed in terms of reduced temperature, reduced pressure, and the eccentric factor, are said to be their generalized equation of state. Kasi maganda yung range of applicability nila for both gases and liquids. Okay, so you can use these cubic EOS for both gases and liquids. Okay, pero the question now here is, diba, if you're solving for a vapor-like root and liquid-like root, it means your system should be at the saturation pressure. But now, how do you determine the actual saturation pressure using a cubic EOS? Okay, so dito papasok yung the second root, okay, for the cubic EOS. So what would that look like? Okay, so recall, ito yung PV diagram natin. Okay, and to obtain the saturation pressure, okay, 'di ba? Below the critical temperature, meron tayong local minima and local maxima. Okay? Now, dapat, okay, ang real behavior, 'di ba, should be something like this, tapos mag-flatten, tsaka siya magde-decrease. Okay? Yan yung real behavior ng mga isotherms below the critical point. But now, the cubic EOS predicts this local minima and local maxima. And the intersection actually of this isobar, okay, with these 3 points, okay, will give you the roots of your cubic EOS. And ang solve natin dun sa dalawang iterative techniques is the saturated liquid volume and the saturated vapor volume. Okay, but now, ano yung significance ng ating middle root? Okay? So, kaya hindi maganda shift solve lang for cubic EOS kasi baka hindi maganda baka ma-solve mong root is yung nasa gitna. And that root has no actual physical significance. However, mathematically, it gives you significance such that, okay, if this is your saturation pressure, dapat, kung ito yung curve natin, the curve bound between this isobar and this part of the curve, okay, of the cubic EOS should be equal to the area of this curve. So these two areas should now be equal. So para mahanap yung actual saturation pressure for using the cubic EOS, okay, kahanapin mo yung isobar such that for each isotherm, madadivide niya into two equal areas yung dalawang to. Okay, so it's medyo trial and error. Okay, or you can use your numerical techniques to find the actual saturation pressures. So for the cubic EOS, hindi masyadong mag-work ang mga Antoine equation natin kasi iba yung Antoine equation sa cubic EOS, sa derivation for the saturation pressure. Okay, so let's have this example, okay, which you should try to do this on your own, all right, before proceeding to the worksheet. Okay, so given the vapor pressure of N-butane, which is 9.4573 bar, so given na yan, you don't have to find it. Okay, find the molar volumes of saturated vapor and saturated liquid N-butane at these conditions using all 4 cubic EOS. Okay, so given the following properties, okay, of N-butane, okay, what you now need to do is calculate for the liquid root and the vapor root. Okay, given, ito yung mga values of A of T and B. Ayan. So, From here, you can actually make an Excel spreadsheet if you want, or you can calculate all of these manually. So for the summary of these calculations, you should be able to obtain the following values. Okay, for the van der Waals, Redlich-Kwong, Suave-Redlich-Kwong, and the Peng-Robinson equation of state. Okay, for the vapor and the liquid route. Ayan. So ito yung pinaka-accurate na solution. Okay? So I think 0.001 or less yung vapor, yung tolerance for the volume. So again, ito yung vapor-like route, ito yung liquid-like route. You can also try solving this in terms of Z. Okay? I'll provide another version of these calculations, or the summary of iterations, or the summary of the values for the iterations in terms of Z. Okay, I'll provide a file for that in the course pack. Okay, ayan. So an example for iteration values should be presented here. So for the Redlich-Kwong gas route, ito yung summary of iterations. And for the Peng-Robinson liquid route, ito yung summary of iterations. So typically, mas mabagal mag-converge ang ating liquid route compared kay gas route. Ayan. So please try solving these on your own. Okay, the iteration techniques are repetitive, so hindi ko napapakita dito sa video. So try solving the iterative techniques on your own. So, similar lang siya sa fixed point iteration natin for temperature, but this time, yung volume na yung ina-iterate natin. Alright, so that's it for our discussion on the cubic EOS, and thank you for listening.